all of you. In this lecture, we will start from the solar photovoltaic array modeling. If you this figure here, this is the mathematical modeling of a single cell. This IL stands for the light current, as we have discussed in the previous class, and this is the diode, and this is the shunt resistance, and this is the series resistance. I want to discuss here that what is the justification, what is the physical significance of these two resistances. One is the shunt resistance and the second one is the series resistance. And finally, if you will see here, I have written V cell, this is the output port, port 1, port 2, from where basically we take out the current to the external load. If it is a resistive load, so the current will flow from here and it will flow through the load and come back to the cell. Now, this is what I cell stands for cell current and V cell stands for the cell voltage. First, I will come to this shunt resistance. The symbol of this is RSH. Why it is shunt resistance? Because it is connected in parallel across this diode. That is why it is called as shunt resistance. Shunt means parallel. The significance of this shunt resistance is due to the manufacturer defects. In many literatures, it is written the shunt resistance RSH comes due to the manufacturing defects, and rather than poor solar cell design. This is very important. Sometimes we think it is due to the poor solar cell design. No, it is due to the manufacturing defects. Due to that, this RSH comes, and due to the insertion of this RSH or due to the presence of this RSH shunt resistance, the current flow through this particular device, I mean basically this IL is going to be distributed through this diode and as well as through this shunt resistance. That means the current which is going to flow through the load terminal will reduce, and also the voltage drop will also there. That is what the demerit of this shunt resistance. So, it is always desirable that the construction should be, the manufacturing process of the solar should be proper, should be perfect. Now, coming to the series resistance, this is denoted basically RS, this is denoted by RS. So, this particular resistance RS is connected in series across the load. If it is here load, resistive load let us say. So, across this load, this resistance is in series. That is why it is known as series resistance. And what is the reason of this series resistance? Why this series resistance comes to picture? The first one is, it is due to the movement of current through the emitter and base of the solar cell. We have electronic devices, there we have emitter and base. Due to the movement of current, you know that to the flow of current, the current is basically the opposition is there, that opposition is nothing, the resistance. So, due to that opposition there may be some resistance, and the contact resistance between the metal contact and the silicon. I have shown in the previous figures that we have PN type junction and there just below the silicon type, P type or N type, we have the metal contacts. So, due to the contacts, some resistances are present and that resistance also contribute as a series resistance. And the third one is the resistance of top and rear metal contacts. In the top we have a metal contact and the below of the solar cell we have one metal contact. Due to these two metal contacts, we have also this resistance. So, due to all these three, when these are combined, we have this series resistance. And the main impact of series resistance is to reduce the film factor. This is a very important point. due to the presence of this series resistance, the film factor will be reduced. We will discuss more about this film factor when we will come to the characteristics of the solar cell. The film factor is nothing, it is a ratio of the short circuit, this voltage and current, I mean the numerator, this is the film factor, this is the numerator, the output power divided by the the short circuit ISH into V open circuit. This is the short circuit current and output voltage, that is open circuit voltage power, and this is basically the P max, basically this is V max into I max. So, this ratio is known as the film factor. Due to the presence of this series resistance, the film factor will be reduced. In fact, if the film factor is near to 1, it will be treated as a good cell. If it is, basically this film factor varies within 0.7 to 0.8. That means we will discuss in more detail in the subsequent slides. If the film factor is close to 1, that means it is a good cell, the performance is better, the efficiency will be better. So, basically this series resistance reduces the film factor, and although extensively high values may also reduce the short circuit current. If the series resistance value is very high, then it may also reduce the short circuit current, I short circuit current, the short circuit current of the solar cell. Now, we will just derive the current equation at this point. You see, this is the incoming current, this is here IL, and here it is one node, this is ID, outgoing current, and at this node the outgoing current is ISH, and here the outgoing current is I, basically sometimes we also write I cell, and this is V cell. I am talking about the model or equivalent circuit, electrical equivalent circuit of a single solar cell. In terms of model, in the place of model, we can use the basically the equivalent circuit, electrical equivalent circuit of a single solar cell. Now, by applying this Kirchhoff's current law, that is KCL, so at this point of the junctions, these 2 points are equal. So, at this junction, the IL is equal to, the incoming current is IL is equal to the summation of the outgoing currents. The outgoing currents are basically ID, ISH and I cell. So, this is how I have written here, right. So, if we will just write this I cell, first I will write here IL is equal to ID plus ISH plus I cell, or here we have denoted I. Now, this I cell is equal to IL minus this ID minus ISH. That is how, this is the first equation and this is your second equation and this is your third equation. Now, what is this third equation? Here it is IL and this is your diode current. Basically, this IL is the light current and this ID is the diode current and ISH is the current which is flowing through this shunt resistance. Now, this diode current is like this, I naught into this exponential of V plus IRS divided by this theta into Vt. So, that is how this is our output current, or we sometimes call it I cell, and this is your IL photo generated current, ID is the diode current and this is your shunt current and this is the diode ideality factor, and this Vt is basically the threshold voltage of the diode, that is basically in the range of 0.0259 volt. And what about this? This is basically our ISH. How to determine this current? Basically, the voltage here is plus minus V cell, or sometimes we call it V. And this is the voltage and here is the current I. So, drop here, I mean after the drop across this resistance is how much? IRS. Now, if I will add this drop and this voltage. So, I will get the voltage across this RSH. That is what I have written here, V plus IRSS. So, this is how we can define VSH is equal to V plus IRS divided by RSH. This is the voltage across this resistance and this is the resistance. This is, it should be ISH not VSH. This is the resistance of the shunt resistance, and if we divide voltage by resistance we will get the shunt resistance current. And by replacing this ISH in this equation 3, so the final equation looks like this. Now, here the if you have the presence of shunt resistance which is quite, I mean the in terms of magnitude it is larger than the series resistance. So, we can sometimes neglect the impact of series resistance. So, here in the numerator the RS term will be absent, and similarly in this case also. Now, coming to this one abbreviated equation, here the G stands for Q divided by AI KT. This is the electronic charge and this AI basically the idle factor, sometimes it is eta, some symbols basically use, some papers, research papers differ different notations, and K is basically the Boltzmann constant, and T is the temperature of the cell, and this is the I cell output current, and V cell is the cell output voltage. Already we have discussed in the previous slide. Now, what is this I naught? We have not discussed till this point. This I naught is basically a cell saturation current. This is very important. Cell saturation current, it may be in the forward direction, may be reverse direction. Now, this I naught can be written as I naught R into this T divided by TR to the power 3 into this exponential Q Eg0 Bik whole this 1 upon TR minus 1 upon TT. Now, if you will see, all these symbols are very easy which are written here. I can say one by one. This TR in this equation stands for the reference temperature, basically it is 301 Kelvin, and I0 which is written here, that is the reverse saturation current at TR. At that particular temperature, what is I0 R, and the value is this much, 19.9693 into 10 to the power minus 6 ampere, and Tc is the cell temperature, and we have Ki short circuit. See, this K stands for the short circuit current or temperature, and this is basically the magnitude 0.0017 ampere per degree Celsius, right. And then we have next further this, if we will explain this IL, how does it look like? This is basically I short circuit plus K I short circuit Tc minus 28 into RAD by 1000, right. So, this is basically the Tc is the our cell temperature, and this Tc is basically written in this term TAR plus 0.3 into RAD. This RAD is the cell illumination, basically the cell illumination rate unit is watt per meter square. If it is 100% illumination, so that will be 1000 watt per meter square. Also, we have short circuit current at 28 degree Celsius and 1000 watt per meter square, that amount is 2.52 ampere. And what is this EG0? That is basically the band gap for silicon, and the value is 1.11 electron volt, and T air is the ambient temperature of in degree Celsius. So, these are all symbols and some parameters we use to express the saturation current of the cell and the light current of the cell. This is very important. I will discuss about what is this short circuit current. If we will come back to this particular module, mathematical equivalent, I mean this is basically the electrical equivalent of the solar cell electrical circuit. If we will sort these two terminals, the current which is going to flow is known as short circuit current, and if we will open it, these two terminals, the voltage which is going to be available, that voltage is known as open circuit voltage of the cell. This open circuit voltage and I short circuit, these are very essential quantities. When we supply basically the solar panel, when the manufacturer they manufacture the solar cell or solar panel, definitely they have to specify the value of these two quantities, the open circuit voltage and short circuit current of the solar panel. Now, so these are the basically the expression for this saturation current and the light current, and these are corresponding symbols. Now, let us say we have more number of cells which are connected in series and parallel. To have more power, because a single cell produces 0.5 to 0.6 volt DC. So, if we need more voltage, more power or more current, so we have to basically make them in series or we have to connect in parallel. So, that means if the number of cells increases in series or parallel, so what will be the expression of our current? This is our expression. This IPV or I cell is equal to NP into IL minus NP into I naught. The only difference here is, in place of this light current, we have multiplied one term, that is NP. This NP stands for the number of panels connected in parallel. I will tell why we have multiplied here NP, not NS. NS is the number of cells connected in series. Let us assume in this particular panel we have this NS number of cells connected in series and NP number of cells connected in parallel, let us assume. And next here minus NP into I naught, and these terms already we have written in the first equation, and this is the basically the current which is flowing through the shunt resistance. Now, here one change, I just said why we have multiplied this NP with IL. The light current is multiplied with NP and this saturation current is also multiplied with NP. The reason being, if you see, if we have a parallel circuit and we have a source, then this particular source, in this particular source we have like I1, I2 and I3. This is I1, I2 and this is I3. So, current will be added. This I total is equal to I1 plus I2 plus I3. That means, if you will connect number of cells in series, I mean the voltage will increase. If you will connect more number of cells in parallel, then the current will increase. That is why this IL, the light current, is multiplied, it is increased by NP times, and similarly this saturation current is also increased by NP times. In parallel circuit the current increases and series circuit the voltage increases, that is the reason. And these are the symbols, and this is how it looks like. I cell is equal to IL, I naught, EXPG V cell plus I cell RSL minus 1, and the relationship is like this IPV. If you multiply this if number of cells are in parallel more, that is NP, the expression will look like this. Now, I will come to the VI characteristic of the solar cell. This is the curve which shows the VI characteristic and also the PV characteristic of the solar cell. Now, along this x axis we have taken voltage and along y axis we have taken current. Now, I will just explain the blue one. This blue one is basically, this blue line is basically our VI characteristic. Why this characteristic is like this? If you could see here at this point along the x axis, I will start from here first. At this point the voltage is basically how much? The voltage is 0 here, and this voltage, the current is 0 here, the voltage is maximum, and that voltage is known as open circuit voltage. This is the open circuit voltage. Here the current is 0, I is equal to 0. If the current is 0 and the voltage is VOC, then the P will be VOC into I is equal to 0. And come to this point here along the y axis. At this point the current is basically called as short circuit current at this point. And what is the voltage status? The voltage equal to 0. Now, if you multiply this 2, the P is equal to V into I short circuit, that is equal to also 0. That means at the starting point, let us say from the y axis, here it is, the power is 0 and where we have the short circuit current position, and here also the power is 0 where we have the open circuit voltage position. That means at the two terminals, two corners, I mean the two top points of my VI characteristic of the solar cell, the power is equal to 0. Now, you start slowly, if you see the VI characteristic remains almost constant throughout, and then it reaches to this point where there is a circle, and this point is known as maximum point MP, maximum power point MPP. We call this point as MPP. And further if we will decrease, I mean go ahead, the voltage increases, that means the curve is now falling down and it touches to the VOC. And that is a great significance, I mean why this characteristic is like this. If you will see the previous electrical equivalent of the solar cell, let us say we have here is the cell equivalent and here we have the load, this is the load. Now, let us say I will just make this load quite large, I mean the resistance of this load will be quite large, maybe near about towards it tends towards infinity. Of course, it will not be infinity, it is not feasible. Basically the open circuit system, I mean open circuit terminals basically behave as a infinity resistance, the impedance is infinity. Now, if this load resistance is very high, that means the voltage available across these two terminals as if it will be treated as the open circuit voltage. And obviously, as this resistance is very large, the current flowing through this circuit will be 0. And further what I will do, I will just reduce this resistance of the load. I will reduce the resistance of this load, and what will happen? Slowly when this resistance value will be reduced, now the current will try to flow through this circuit, the current will try to flow through this circuit, and when the current will flow, so there will be some drop across this load. So, how to this voltage, what will happen to the voltage across these two terminals? We are measuring the voltage across these two terminals. Now, the voltage slowly it will fall. Now, if we will start from this VOC, now the voltage will fall and it will reach to certain point where it is treated as VMP. Why this voltage is VMP? I will just come when we will come to this particular PV characteristic. This is the point or voltage where the maximum power exists, that is why this voltage is known as VMP. And then further the voltage drops and again the voltage drops and comes to this point, and here the voltage is 0 when this load is, the resistance is almost negligible and path is totally short circuited. What we have started? We have started from a very high resistance to a low resistance, almost short circuit path, then the curve starts from here and ends here. At this point we will get the short circuit current, and the voltage across the terminal of this particular two terminals, the voltage is going to be 0. Now, that is how, I mean the way I can explain how this IV curve looks like. Now, if we come to the PV curve power versus, if you see here we have just written this P in watt, because output of this solar cell is in watt. This watt is along x axis, y axis, and along this x axis we have voltage, and along y axis we have taken the power, which is in watt. Now, this how to get this PV curve? Just you keep on multiplying this voltage into current. This is basically the current. So, let us start from here. This is a 0 point of the, this is the power is 0 here, P is equal to 0, because the voltage is 0, current is 0. Now, again I will just multiply this voltage, this current, again I will multiply this voltage, this current, again I will multiply this voltage and this current. So, I will get the corresponding power throughout this particular axis. This is the trend of the PV curve. Now, at this point I will get the maximum power, and if you will see here that this is my short circuit at this point, the short circuit current, and here is my V, because it is along the x axis VMP, and this current at this point where I got the maximum power at this point, this is basically the corresponding current IMP, because I am keep on multiplying the both V and I. So, at this point I will get the power multiplication of this VMP and IMP. It may reach to this point, not necessarily this PV curve will be below my VI curve. If you multiply this VMP, IMP, I will get this one, this point, that is known as MPP. Now, if you just see this rectangular dotted line rectangular area, let us say this is my area number A, and this one if I will just start from here, I short circuit and my open circuit voltage. So, this area is basically area B. That means the area A is basically due to the multiplication of VMP into IMP, and area B is basically due to the multiplication of VOC into I short circuit. So, which area is greater? The area covered by this V open circuit I short circuit is greater than this area, that means B is greater than A. This is how this VI characteristic, PV characteristics and VI characteristic of a solar cell looks like. Now, coming to this, these are the few specifications basically provided by the manufacturers. The first one is the short circuit current, and the second one is the open circuit voltage, already we have discussed, and this is basically the maximum power point voltage, and this is the maximum power point current. I just want to mention here one point or one thing I just want to share with you, that as far as the solar cell is concerned, its operation, its efficiency is concerned, these 4 quantities are very important role. I mean, they play a great role. When there is a word we will not discuss in this particular module, the maximum power tracking controller, MPPT, maximum power point tracker. We have developed a, I mean, different researchers, they have developed different controllers to develop, I mean, to access, to harness the maximum power from a solar cell, because obviously we have designed some solar cell or solar array or solar module, we have to harness the power at the maximum point, not at the minimum or below that. So, for that we have to have a control strategy. So, every time we should take at the maximum point, I mean maximum power should be available to the load. So, that is what the MPPT stands for, I mean the function of the MPPT algorithm, maximum power point tracking algorithm. And of course, if every manufacturers, they basically all the manufacturers, they provide the specification sheets, and where this I short circuit, V open circuit and maximum voltage, power point and current all are mentioned. What is this maximum power point? This is a multiplication of these two quantities IMP and VMP, and this is basically the sometimes peak watt, sometimes we write WP, peak watt also. The unit sometimes it is also peak watts, the unit is watts. And what is this film factor? The film factor is the ratio of two factors. I mean the first one is this one power, ratio of two powers. This is power P1 and this is P2. The P1 is the multiplication of V max P and I max P and this VOC into I short circuit. Remember always this P2 is greater than P1 and obviously this VOC, the open circuit voltage of the solar cell, is greater than the V max, maximum power, the voltage corresponding to the maximum power, and similarly I short circuit is greater than I MP, the maximum current. I mean the current correspond to the maximum power point. It is not maximum current, it is a current which correspond to the maximum power point. The ratio of these two powers basically known as the film factor, and this specification is also provided inside the solar panels or sheets, and this particular factor lies between 0.7 to 0.8, and this if it is close to unit, that means we are using more power. The P max, if this P max is much more, closer to this VOC into I short circuit, then that means if it is very close to this, we are harnessing more power from the solar panel. Now, what is the efficiency of the solar cell or solar array or module? The efficiency is nothing, that is the ratio between the maximum electrical power. The output of the solar cell is electrical power, that should be the maximum power, with respect to the compared to the amount of solar irradiance hitting the array. This is the important. The irradiance we will discuss in the next slide. The irradiance, that is a maximum, what is the amount of solar irradiance hitting to the array. That means the electrical energy, the electrical P electrical is the output and P light, that is the irradiance. Irradiance means the power intensity of the solar cell, the sunlight. So, that is the input power and this is the output power. That is what the efficiency of the solar cell, and this efficiency particularly lies in between 10 to 12%. Now, this is very interesting characteristic. Here I just want to explain that if let us say more number of cells are connected in series or parallel, how this VI characteristic will look like or how this PV characteristic will look like. Let us say this is the single, this blue one is the VI characteristic when the cell is single. This is the maximum power point characteristic, the point, and this is the corresponding VMP and this is the VOC and this is the corresponding I short circuit. And now also we can, if we multiply the voltage and current, then of course we can always obtain the power PV curve. Similar also we can do for the other two. Now, you come to when the cells are connected in series, this is how it looks like, the curve VI characteristic. Now, what will happen? This VOC will shift to this point and here this I short circuit remains constant. This is very important, that when the cells are connected in series, then the voltage increases and the current remains, the short circuit current remains almost constant. However, the power, the maximum power point shifts to another point. If you could see here, in a single cell, this is the maximum power point position, but here in this case the maximum power point position is here. The area covered here is less and the area covered here is more. Now, this is how this MP1, this is MP1. Now, if the cells are connected in parallel, then what will happen to the I short circuit and open circuit voltage? If the cells are connected in parallel, so this is how the short circuit current at this point ISC 2, this is ISC and ISC 1. Now, this is the VOC point, this VOC is equal to VOC 1. And what about the maximum power point? That point also shifts to another. Is it shifts? No, it is the same as our previous maximum power point, here it is. So, only the magnitude changes, I mean the voltage remains, VMP remains constant, I short circuit changes and V open circuit remains constant for this. So, what is the basic difference between this parallel series combination? In case of series, we have this different VOC, because in series connection the voltage increases, and in case of parallel combination the current increases. So, that is why the I short circuit 2 is greater than this I short circuit 1 or I short circuit, and similarly if you will see the power also jumps to another level. Here is the power axis and the power was here P 1, now the power is here P 2. Obviously, this P 2 is greater than P 1, right. So, that is how the series and parallel combinations are basically decided to get how much power we desire, how much power we need for our particular load. So, accordingly we can design or we can place the solar cells or modules or arrays in a proper manner. This is one of the specification sheet provided by the Tata Power. The model name is TS230 MBT and the power output, this is a maximum power output 230 watt, W stands for watt, and the VM stands for the maximum voltage, that is 29.1 volt, and the IM is the maximum current, that is 7.9 ampere, and VOC is in volt 36.7, and I short circuit is basically 8.4. If we will go for the film factor here, it will be how much? It is the multiplication of V max into I max divided by VOC into I short circuit. Then this V max is 29.1 into the 7.9 divided by 36.7 into 8.4. So, more or less this value will be obviously less than 1, because if you could see here in this case the VOC is greater than VM and I short circuit is greater than IM. So, that is why this value, the film factor will be less than 1. Now, in the subsequent 2-3 slides we will discuss about what are the impacts of temperature and the irradiance on the VI characteristics or PV characteristic of the solar cell. First of all, I just want to explain first the impact of irradiance. What is irradiance? The term irradiance is defined as the measure of power density of sunlight received at a location on earth and is measured in watt per meter square. The unit of this irradiance is watt per meter square. This is basically measure of power density of sunlight, that is irradiance. Now, what is the difference between irradiation? It is the measure of energy density of the sunlight. These two are two different terms or phenomenon. This is the energy density of sunlight and this is the power density of the sunlight. Now, the question comes, if I will increase or decrease the irradiance of the sun, I mean irradiance, then how it will affect my IV or VI characteristics and PV characteristic positions, whether it will remain same or it will be different. Now, let us come to this IV curve first. Here you could see here we have blue, red, green and purple color lines, IV characteristics or VI characteristics, and if you are increasing, the first one is this first characteristics, blue one is 1000 watt per meter square, the irradiance, and second 800 watt per meter square, third one 600 watt per meter square and the fourth one is 400 watt per meter square. Now, if this irradiance increases, this increases from 400 watt to 1000 watt, that means my short circuit current level will keep on increasing, and however, here the open circuit voltage this VOC, you know, this is our VOC and these are my short circuit current positions. These are my short circuit current positions. Now, why it is so? What is the reason behind it? Why this short circuit current increases in a wider range? However, this open circuit voltage remains almost constant, but increases. This VOC also increases, but in a logarithmic scale the change is less in comparison to your short circuit current. What is the reason behind it? The reason behind it is when this irradiance increases means the measure of power density, the power density in the sunlight increases, that is called as photons, photon increases. I mean this power density increases means that means the current, I mean the electron pairs increases more and then the current flow will be more. That is why the short circuit current magnitude is going to be increased and the voltage remains almost constant here. Now, coming to the PV characteristic, in case of PV characteristic, here you see that if the irradiance increases, that is from 400, 600, 800,000 watt per meter square, then the corresponding maximum power point also will increase. In the first case it was in A position, this is B position, C, then D position. Now, that means if the power which are getting at 400 watt per meter square will get more power at 1000 watt per meter square. And here you see the temperature is remained constant 25 degree Celsius, the temperature is not varying, only the irradiance is varying. Now, we will come to the impact of temperature, how this IV curve and PV curve will look like. If the temperature, see here we have taken in degree Celsius, 0 degree, 25 degree, 50 degree, 75 degree. The temperature varies, then the VI characteristics, if you see, the short circuit current remains constant and your open circuit voltage VOC will vary. If the temperature is high, then the open circuit voltage will be less, and if temperature is low, then the open circuit voltage will be high. This is because during the temperature the photons rate increases and the reverse saturation current through the diode increases, and as a result the band gap will also reduce. Due to that, this VOC will be reduced. More temperature, the less open circuit voltage, I mean the less power basically. The temperature, increase in temperature is not desirable for the solar cell. If you see many literatures, it is written, I mean it is also obvious that if the temperature, it is a very cold and sunny day, that the power generation will be more, and it is a very hot and sunny day, then the power generation will be less. That is the meaning of this particular IV curve as far as the practical system is concerned. Now, coming to this PV curve, the similar thing happens, that if you just increase this purple, green, red and blue one, this blue one is for basically 75 degree Celsius, the higher temperature, the lower temperature. Now, similarly, if the temperature is higher, the power generation also will decrease, because our VI characteristic says that, because VOC decreases and here basically the corresponding power also decreases. Now, this is also important characteristics where both will vary. If the temperature and irradiance both will vary, then how this VI, I mean the PV characteristic looks like. It is here this 75, these two curves are for 75 degree and these two curves are for 25 degree. And we have taken here 1000 watt per meter square and other one is 400 watt per meter square. And this is, these two are the irradiances, and the temperature one is 25 degree, other one is 75 degree. If the temperature, see this is the 75 degree temperature, these two, the red and the purple one, the red one and the purple one, this is the red one and this is the purple one. So, here the temperature is 75 degree, that is why the peak current, I mean the power is basically reduced in comparison to the green and blue one where the power is higher than these two. It is obvious. And as far as the irradiance is concerned, 1000 watt basically this one, this 1000 watt is the blue one, I mean the red one, and the purple one is 400 watt. Okay. So, what is the meaning of this? If the irradiance is higher, that means 1000 watt per meter square, and the irradiance here is 400 watt per meter square, then the power basically decreases if we will go for the lower irradiance. Higher irradiance means more power. Now, these are the references what we have covered here in this particular module. So, let us come to the conclusion. In this particular lecture, we have covered the electrical equivalent of a particular solar cell, and where also we have discussed that what are the significances of the series and shunt resistances which are present in the solar cell, and also we have derived the corresponding saturation current and the corresponding light current which is basically present inside the solar cell. This I naught is basically the reverse, I mean the saturation current, and IL is the basically light current. Now, also we have after that we have discussed the VI characteristics and PV characteristic of the solar cell, and also we have discussed if the solar cells are connected in series or parallel, then how these two characteristics will vary, and also in the last we have discussed what are the impacts of this temperature and irradiance on the VI and PV characteristic of the solar cell. Thank you all.